Thank you very much, Al. Thanks for having me. And yes, indeed, please do interrupt with any questions or comments. I appreciate the discussion. Okay, so this is a project together with Johannes Müller, a PhD student at the Max Planck Institute for Mathematics in the Sciences in Leipzig, Germany, who indeed has done most of this work. Okay, so let me tell you about the situation that we're looking at here. We're thinking about a sequential decision-making problem situation where we have an agent that is interacting with an environment and is doing that by way of taking some observations, and based on those observations, choosing some actions. So it takes an action at every time step, and that influences the environment. So in turn, the observations that come next are influenced by those actions. So there is a loop going on. And note this is a little bit different from the situation where you are just solving a classification problem where the input data to be classified is, let's say, assumed to come from the same probability distribution all of the time. Here, every time that we select an action, we're influencing what's going to happen next, the data that we're going to observe next. So there is this kind of feedback happening, and we want to figure out a good action selection policy for this agent. And we're going to be thinking about this as illustrated here in the left part. So we have a space of parameters. Those are our search variables, and could be the weights of a neural network. And we're going to imagine that these parameters are going to be mapped to some type of a model. So maybe in a classification setting, you could say this is going to be the actual functions. So this would be a realization map. Some people call it that way. But here it could also be just the policy itself. So the actual action selection mechanism, that is the probabilities for individual actions given individual observations. This is a mapping from parameters to conditional probability distributions. And we're going to have a loss function, capital L, that is defined on the parameters, but in reality, this function only depends on this model. So on the actual hypothesis that we are parametrizing. So here you could imagine that the performance of this agent really doesn't care what is the particular choice of the parameters, but it cares about the action selection mechanism. So therefore, we have this sort of factorization with a loss function here defined over this model space. And so this is kind of the intuition here, or the perspective that we want to exploit, because many times the optimization, so we use the parameters because that's convenient, but the objective function or the criterion that we're trying to optimize is more naturally defined in the model space. So many times the optimization problem over here will be convex or have nice properties, whereas the optimization problem over here may be complicated and convoluted. Okay, so parameter space and function space, as I was saying, often we have a parameterized set of hypotheses, let's say P theta, where theta is our parameter in some parameter space, capital theta. And this set, we're going to be thinking of it as a subset of this M. And we're seeking to optimize an objective function of the form capital L theta, which factorizes, which can be written as little l of P of theta. We're interested in P of theta star rather than theta star. With this in mind, it certainly sounds natural that we may want to use the steepest direction in the model space in M rather than using the steepest direction in the parameter space theta. Somehow the parametrization of our hypothesis is a little bit arbitrary. So we could choose to parameterize a function with some type of constant pre-multiplied by to search variable, to the parameter. And, so we could rescale things in a way that is pretty artificial. But the model, so the space where this loss is defined naturally, that could be a little bit more natural. Now, so therefore, the idea of using the steepest direction in M rather than capital theta. If we want to do this, we still need to decide how to define the geometry on M. Right? So because if we want to talk about a steepest direction, we need to have a way of measuring lengths of vectors. And so a geometry. In this project, in this work, what we did was to study a variety of different gradient methods that are defined with respect to different geometries, with respect to different factorizations of this loss function, and the context of the sequential decision-making problems. This is an overview of the results that we obtained, highlighted in bold, that are the contributions from this work. So there's the standard ordinary gradient method, and there are several classes of so-called natural gradient methods for which in discrete time and continuous time we look at the convergence. So we are able to prove that these methods converge to an optimal solution at a particular rate. In this case, it's linear. In some other cases, sublinear. And if we have a regularized setting, we regularize the objective function, we are able to show quadratic convergence in discrete time, linear convergence in continuous time for the gradient flow and gradient descent, respectively. Okay, so this is a topic that has received kind of an incredible amount of attention very recently. And so there are a series of results that have come out related to this. Okay, so this is the overview. I'm gonna tell you briefly about Markov decision processes and the natural policy gradients, and then briefly show you our results on the convergence of the natural policy gradient flow and the quadratic convergence for the regularized natural policy gradient. Okay, so Markov decision processes. I already mentioned we are in the situation where an agent is interacting with an environment sequentially, and we want to optimize the action selection mechanism that we call a policy. More formally, we're going to have a set of states, say the states of the environment, a set of actions. These are the actions that are available to the agent. We're going to be assuming that these are finite sets. And then we're going to have transition probabilities. Well, if we have the environment in state S and the agent selected action A, then there will be a conditional probability over the next states of the system, and we're going to call that alpha. So it's a Markov kernel or a conditional probability distribution. And then we will also have an instantaneous reward, little r, which is a function of the state and action pairs. Whenever the agent takes an action A and the environment was at state S, the agent is going to receive an instantaneous reward, little r, of S and A. I'll show you in just a moment that so the objective function is going to be trying to look at the aggregated instantaneous rewards over time, and that's the thing that the agent is going to want to optimize. And so the agent is going to have policies available. We're going to be looking at the class of memoryless stochastic policies. So for any state, the agent is going to be able to select an action with some probability. So what the agent is trying to figure out is what is the correct probability distribution over actions given states. So the search variable, this will be a stochastic matrix or Markov kernel in the set of Markov kernels that map from S to A. I should point out, I'm going to be focusing here on the case of that is called fully observable case. That is when the policies, they are looking at the state and selecting an action based on that state. But more general cases that we also study and are very interested in are partially observable Markov decision processes, where the agent first makes an observation of the state through a Markov kernel. And then based on the observation, the agent selects an action. It's a little bit more complicated, but I won't discuss that today. Okay, so this is the diagram. We have this sort of graphical representation of this process. So whenever we fix a policy, this induces transition kernels that map state action pairs to state action pairs, like here. So we have the state at time t, the policy gives us a probability distribution of actions, and the state and action gives us a probability distribution over the next state. And these conditional probabilities, we denote them by alpha. So we can define this kind of Markov transition for the pairs, or we could also look at the Markov transitions just for the states themselves if we marginalize out the actions. All right, so as I mentioned, at each time step, the agent receives an instantaneous reward for taking an action A at the state S, and we want to optimize the long-term reward. So we're going to be looking at this quality criterion, which is the expected discounted reward. So we look at all these instantaneous rewards at different times, from time t0 to infinity, and we're going to discount the reward at time t by a factor gamma to the power t. So things that happen far into the future are discounted, as we're going to be looking at gammas between 0 and 1. And there's a normalization or scaling factor here, and then we take the expectation with respect to this stochastic process through the sequence of state action pairs over time. Since everything here is stochastic, it's a good idea to take that expectation. I should mention, for this to make sense, we also need to stipulate an initial probability distribution over the states. I'm calling that here mu. So at time 0, the distribution over the states is mu, and then we start applying the policy and these transitions. So this generates this process, and we just accumulate those instantaneous rewards and take the expectation value. So it's a very standard objective function or criterion to consider in this context. There are some other versions of this. Maybe you don't want to discount the rewards into the future. That would mean more or less that you take the limit of gamma to 1. So this discount factor disappears from the picture, and we just get the average reward over time. So some of the important properties here are, so this objective function is a function of the policy pi, which is the stochastic matrix of conditional probabilities for the different actions, given the different states. As a function of that, of the entries of that matrix, this is a non-convex, and it is actually it's a rational function. So it has some nice properties, but some other properties that are not super easy. Okay, so one key observation here, and keep in mind this factorization that I was telling you about for the loss functions that we want to, that kind of motivates our analysis, our perspective. So this reward function actually can be written in this other form, where we still have here the instantaneous rewards, but we're looking at the linear function. We're looking just at the sum of those instantaneous rewards for some eta, and we could even write this just as this inner product. So it's a linear function of eta, just inner product with the instantaneous reward function. So what is this eta? So this eta is just collecting everything that we took out from that previous formula. So we just take for eta, we aggregate all the probabilities for the individual state action pairs over time and discounted over time. So this can be interpreted as a discounted stationary probability distribution over states and actions. It's called a state action frequency. All right, so we can actually always do this. One funny thing that happens is that, of course, our original search variable is pi, and now we have this thing that can be interpreted as a function of pi, and it will have some range. So not all values of eta may be possible, may be feasible. So we cannot modify eta at will because it may attain only or a constraint set of feasible values. Nonetheless, the optimization problem is now linear in eta. So that's what I was talking about, that you have this objective function, and maybe in one perspective it is complicated, and if you represent that search variable in some other space, in this case we're representing the policy in terms of the state action frequencies, the loss function becomes easy. So in this case it is easy because it's linear. So the idea is then to study the problem over eta and consider the factorization. So we're mapping the parameter to a policy and the policy to a state action frequency and to a reward. So we're going to consider this thing here as our model space. Okay, so any comments, please jump in or type them in the chat. I will be monitoring the chat. Fine, so for Markov decision processes, where we have, we don't have this issue with partial observability, we're looking at the state directly. And it's actually pretty nice because the set of feasible values of eta actually, even though it is not everything, it is not the set of all possible probability distributions over states and actions, it actually is a convex set, and in fact is a polytope. So the set n of state action frequencies is a polytope, and it is given by the intersection of the set of joint probability distributions over states and actions and this L, and L is an affine space. All right. So here, as an affine space, that's the set of solutions to a collection of linear equations. So these are the linear equations in eta. And essentially what they are telling us is something like eta should be some kind of a stationary probability distribution discounted into the future. So, and but so we intersect an affine space, and the set of probability distributions over S and A being finite sets, this is actually a simplex. It's a polytope, so the whole thing is a polytope. And in turn, when we think about solving this Markov decision process or optimizing this expected discounted reward, this should be equivalent to solving a linear program over eta. Now mind, when we do our optimization, typically we're optimizing over the policy pi, not eta, but the mapping from pi to eta is a rational map. So we're trying to do gradient optimization over pi, but we have this kind of rational map sitting in between. So maybe an illustration here. So the policies, the conditional probability distributions, they form a Cartesian product of probability simplices. Here, this would be an example for the product of two one-dimensional simplices, which is the square. And so in the case that we get to observe the entire state, so we can look at the policies depending on the states. And this again is just the same square, but we're mapping this via a rational map to the space of state action frequencies. And the point in the previous slide is that this image is a polytope. That would be this polytope right here. And over here, the optimization problem is linear. So because we had here, the optimization problem was given by something like the inner product of R and eta. So if the domain of eta is a polytope, we get here just a linear program over that polytope. And this is illustrated down here. So the mapping from policies to the objective is a rational function, but here over the space of state action frequencies, it is linear. Okay, so we're going to make a couple of assumptions. One is that the state action frequencies, they satisfy this property, in a sense telling us that the probability of the different states, for every state, the probability is positive that it will happen for any policy. This assumption is satisfied whenever we have a strictly positive initial state distribution. And so in that sense, it is not very restrictive, and indeed it is required for global convergence of policy gradient methods. We will use this in order to have a diffeomorphism between the space of policies and the space of state action frequencies that may emerge from those policies. So indeed, if this is true, then we have that the mapping from policies to state action frequencies is rational and bijective and has a rational inverse that is given simply by conditioning. Hey, so then as a quick overview of Markov decision processes, let me move on to the natural policy gradients, and starting with natural gradients. Again, this is the picture we have in mind. We have a space of parameters where we are maybe intending to conduct the optimization. Those are the things we deal with, the parameters. But in reality, our objective function is maybe more naturally defined over the model space. Maybe over the model space, it is a nice function. Okay, then to talk about natural gradients, we should discuss briefly Riemannian gradients. So Riemannian gradient, let's look at it like this. So we're going to want to consider the steepest direction or improvement direction of our objective at the parameter value theta. And what that means is that we're going to want to solve, in a sense, this problem. We want to find the direction or the change in theta so that when we modify our current parameter theta by adding that direction, d theta, this is going to get as small as possible or as large as possible. And we need some type of a constraint here. So we should say that this direction or this change in the parameter, it should have a fixed length. So we consider the length of this modification. Let's say we fix it to be equal to, well, the square length to be epsilon squared. This is a constraint optimization problem. And if we have now a Riemannian manifold, so let's say that our parameter space, the way we measure the length of these modifications of these vectors is via a Riemannian metric. So that is this expression here. So the square length of d theta is given by this expression, where we have here our Riemannian metric. So, if we were in the naive setting, Euclidean metric, we would of course just consider in the product. So this would be a diagonal matrix, the identity matrix. So Gij would be equal to delta Ij. So we would have here just the sum of the squares of the components of the vector d theta. But generally, this is the way it would look like. And if we have this and we look at this condition, we can actually conclude that the steepest direction is d theta, that is going to be proportional to the standard gradient of the objective L. So it would be just the naive gradient, but it is going to be pre-multiplied times the inverse of this matrix G. Okay. That's the way we would formulate this steepest direction, or we could formulate the steepest direction if we had a Riemannian manifold. Now, the natural gradients, they simply say that we should be considering a Riemannian manifold when doing optimization, and this Riemannian metric should be a natural metric. Okay. So that's the whole idea. So maybe we have an objective function R, so then a natural gradient would take this form here. So we update the parameter, and by adding to the current parameter, this ordinary gradient pre-multiplied times kind of inverse of our Riemannian matrix, and then maybe we're going to have some step size here. So for the sake of generality, I have written here a pseudo inverse for this matrix. And what is going to be this matrix? So when we talk about an actual natural gradient, we don't simply mean some arbitrary Riemannian gradient, but and we have this sort of a factorization thing going on, or we're going to want to pull back the metric for the parameter space from a natural space. And so in order to talk about that, maybe we're going to say that there is going to be this sort of gram matrix where we have a metric G in the space, in the model space, and we're going to be pushing forward the basis vectors in parameter space to a tangent space of the model space. And so this is the matrix that we have here, and here in this definition that I'm writing here. So of course P is the representation of our parameter, is our representation in model space. So this part in here. All right, so a typical example from information geometry is the Fisher natural gradient. And so, okay, you can say it's natural because it's pretty natural, okay? So the Fisher natural gradient, it will consider as this representation of the parameter a probability distribution. And it then asks what is a natural Riemannian metric to define on the space of probability distributions. And that is going to be the Fisher information metric that can be written in this way. So essentially, we're computing the inner product of the tangent vectors. We do that by, multiplying here the components, but dividing by the probability of the individual components or states associated with those components. So the matrix would be written in this way. This would be the coordinates of that matrix. This is a famous, or the most famous case. This is what people actually call the natural gradient. But kind of what we are suggesting here is that there are many ways of talking about a natural gradient, depending on what is actually a natural model space and what is a natural choice of the Riemannian metric on that model space. And this is not obvious in general. Okay, so therefore we talk about a general natural gradient where instead of just looking at the Fisher metric, we're going to take a loss that we presume factorizes, and that we're going to have a Riemannian metric on the model space. And then we're going to define that gram matrix that I was talking about and define this object here to be our natural gradient of the loss L at parameter theta with respect to this factorization and the metric little g in model space. Okay, so as suggested in the previous slides, this actually leads to the steepest descent direction in model space. So we look at the push forward of our natural gradient of the loss function at parameter theta. So we use this natural gradient that's given in the previous slide. We push that forward by the differential of our parametrization of model space. Then in fact, that corresponds to us looking at the objective function in model space at the location p theta. And yeah, so and then we need to project that to the tangent space of our model space at the parameter theta. So it's a little bit of subtleties here, but never mind that. Essentially what that's telling us is that, indeed the intuition that this is the steepest direction in model space is correct. So when we use the natural gradient, we're going to be actually choosing to walk in the direction of steepest increase of the objective as measured in the model space rather than with respect to some arbitrary metric in parameter space. Okay, so as I mentioned, if we decide to walk this path, we still need to choose the geometry in model space. And as I was saying, this is not always obvious. A lot of things have been done in the past, and motivations there are very, very good reasons for using the Fisher metric. But the Fisher metric is defined on the space of product distributions, whereas here in our setting, we actually want to work with conditional probability distributions. So these policies are Markov kernels, so they are not the same as probability distributions. Nonetheless, okay, let's look at the, the very celebrated invariance axiomatic characterization of the Fisher metric given by Chensov. What they said was, so if we have two Riemannian manifolds and an embedding, then a metric or the metric of these manifolds is said to be invariant if the embedding is an isometry, meaning that if we look at the metric in our so this is the pullback of the metric in E prime by this or through this embedding to define it in E. So that agrees actually with the metric in E. So it's an isometry. And then the characterization that Chensov obtained was to show that if you require this invariance condition for all embeddings by or congruent embeddings by Markov mappings, these are very natural mappings between probability distributions, then the only metric that remains left is the Fisher metric up to scaling. So that's a very nice reasoning for why to consider the Fisher metric as a natural Riemannian metric to use in spaces of probabilities. And similar results were obtained later for other types of spaces using certain, like this is for not normalized probability distributions, just like matrices with positive entries. And so this is the book by I and co-authors, which is looking at some extensions of this. It's the book Information Geometry for those who are curious. And okay, so we also looked at some, how to follow this criterion for the case of conditional probability distribution. So what is the invariance axiomatic in the case of conditional probability distributions? So we need to first identify a family of embeddings that are somehow natural, and then require that these embeddings form an isometry for our choice of the Riemannian matrix. So this is something that Lebanon studied before in 2005, and we studied in 2014. And this specifies, or this characterizes certain products of Fisher matrices, metrics. But the choice is not as clear. Maybe part of the reason is because it's not so clear what is the correct choice of the embeddings that one is going to consider to be natural, and for which one is going to require invariance. Okay, so another choice that maybe makes a lot of sense if you're thinking about optimization is to do Hessian geometries. The idea here would be to select the metric based on the optimization problem at hand. Instead of trying to say axiomatically what is a good metric, let's look at the objective function and see if it can tell us anything interesting. And so maybe we take some function that has a positive definite Hessian at every point, and then if we take that Hessian, the positive definite matrix, we can use that to define our Riemannian metric. So we would do it this way. So we would have the Hessian sitting here. Whenever we want to multiply tangent vectors, we could do it that way in local coordinates. So this is called a Hessian geometry. And there are, of course, a lot of examples. The Euclidean geometry would be induced by this convex function, where we're just adding the square of the components of the vectors. The Fisher geometry would be induced by the negative entropy. So we take the Hessian of this, we get the Fisher metric. There are other examples. Itakura Saito, this would be obtained from as the Hessian geometry of the logarithmic barrier function. So let's say you have a constraint optimization problem on the positive cone. So maybe you use this as a log barrier. And in this case, you would obtain that metric. In this work, we consider looking at a family of geometries, and that allows us to include all the previous examples as special cases. We're going to look at these sigma geometries. and that so we look at this type of function. So it has depending on the choice of sigma, we define it in this way or this way or this way. And the resulting Riemannian metric for this is given in this form. And you can immediately see that for sigma equals to 1, this records the Fisher metric, where we're just dividing by the components of our vector x here. But it also recovers the Takura Saito metric for sigma equals 2. And in fact, for the case that sigma is equal to 0, we recover the Euclidean geometry. This just allows us to work in some more generality. Another important case that we need to define here or look at is the conditional entropy, and I will explain in a moment why. So conditional entropy is just another function that we may define on the space of probability distributions. So this guy, the conditional entropy here, well, it's just the difference between the entropy. So we have a jump probability distributions of x and y, and we subtract the marginal entropy. And if we look at the Hessian of this quantity, that actually looks like this. So this is, for clarity, this would be something like, this is 1 over mu x y, and this here is 1 over mu x, the margin. So, and if you recall, so this kind of situation where we divide by the individual probabilities, this is like the Fisher metric. We're somehow looking at somehow a Fisher metric for this joint probability space, and we're somehow subtracting the Fisher metric over the marginal distributions. So we're going to use this to look at a conditional probability distributions. So it turns out this defines a Riemannian metric on the interior of sets like this, where we define the margins. So we're looking at conditional probability distributions, and we define the margins as a smooth function of those conditional probabilities, which is what often will happen in our Markov decision process. If the marginal probability is somehow this stationary distribution over states that is obtained once you fix the conditional probability that maps from states to, well, to actions and states again. So and indeed, this can be interpreted as a few more comments here, but if you're curious, discuss more. Right, so what about natural policy gradients? This was somehow a general picture of natural gradients, and what I was mentioning that we define them as Riemannian gradients, where the Riemannian metric is going to be defined in some hopefully natural way, maybe through some axiomatic or through Hessian geometry. In the case of policies, we will be looking here at softmax policy parametrizations. So it's actually more precisely tabular softmax policy parametrization, where if we call these are conditional probability distributions, and now we want to parameterize them by some Euclidean space. So we want theta to be in R as A in this case, but since these are probabilities, they have to be non-negative. And so we can achieve that by looking at exponentials. This gives us something positive and normalizing. So for every given state, we're going to have here a probability distribution over actions. This is called the softmax parametrization of the probability distributions, and we have one of those for every S. It is tabular because every component of this matrix has an associated parameter, as opposed to having, say, for example, very few parameters and mapping them to a very long vector or very big matrix. Okay, so and then we're going to talk about regular policy parametrizations, and the idea here is that we're going to have a parametrization that is differentiable and satisfies the following condition, that the span of these tangent vectors actually is equal to the tangent space of our space of conditional probability distributions. Somehow this means that our tangent space is filling the entire space. Note we're assuming here that the parameter theta is unconstrained, such as For example, when we say RSA, so the parameter can move as far as you want. So we don't have a constraint optimization problem a priori over the parameters, even though the policies themselves, if you wanted to optimize over them, that would be a constraint optimization problem. And also that this condition does not exclude over-parameterized policies. So we could have more parameters than dimensions in this set of conditional probability distributions. Right. Okay, now it turns out, like, recall our objective function that we had is expected discounted reward. And so this was kind of a complicated object, right? So, I mean, the expectation value of the sum from t equals 0 to infinity, gamma to a power t of the instantaneous rewards. So how do we compute gradient for that? And there is this beautiful observation that goes by the name of policy gradient theorem that tells us if we compute the gradient of that objective function, it can be written in this way. What we have here is this stationary state distribution for the parameter theta. We have here just the gradient of our policies with respect to our parameters. And so this looks almost, yeah, maybe in this line, it's a little bit more direct to see. So recall that we had written that somehow like this, like eta times r. So if we take the gradient of this with respect to the parameters of eta, we end up getting something like this. It's like the product of eta, but now we have here somehow substituted that instantaneous reward by this function q. This is the state action value function that tells us what is going to be the reward if we follow the policy pi theta, and we start with the state S and action A. It's a very frequently encountered object in this context, and somehow otherwise, that's all we need to do. So in order to compute the gradient of this, we just somehow need to substitute this R by this quantity, and then the calculation works. So, this allows us to talk about this more concretely. All right, so what is Kakae's natural policy gradient? This was actually one of the first natural gradients that were proposed in the literature for policies. And what Kakae suggested was, all right, let's choose this metric. Let's just choose it in this way. So it's going to choose here the Fisher metric for every fixed state. So this is, you see that for every fixed state, this is just the Fisher metric. And we're going to weight them by this stationary state distribution. So why not? It's a little bit heuristic. And, in terms of the remaining metric, just looks like this. So then there is this interesting observation that this geometry, Kakae's geometry, can be regarded as the Hessian geometry for the conditional entropy. And that's why I wanted to introduce the conditional entropy before. So if we take, so I guess I just said it. So in particular, the Kakae natural policy gradient is the natural policy gradient induced by the factorization taking the state action frequencies with respect to the conditional entropy Hessian geometry over that space. So, and kind of our idea here, again, is to look at things as happening in this model space with some particular geometry, and for those we can establish convergence guarantees. Actually, Kakae's natural policy gradient has been known to converge at a locally quadratic rate under conditional entropy regularization. So we want to study this then also in some other cases. Right, so I should mention that interestingly enough, if you look at the optimization problem in parameter space, then the metric that you're looking at is not the Hessian geometry induced by the conditional entropy. So you would only have that if you look at this as happening over the space of state action frequencies, which is what we're suggesting that is more natural to do. Like in the case that you wanted to do this over the policy space, actually, you would be missing a bunch of terms that are not present in the definition. Okay, what about there is this other kind of famous, important choice of the natural policy gradient by Morimura and co-authors. What they decided to do was say, instead of taking the choice from Kakade, let's actually use the Fisher metric in the space of state action frequencies, which are joint probability distributions. So you no longer have the issue of what happens with the conditionals and etc. I'm just going to take here, recall this was pretty much the definition of the Fisher information metric, and now just over the space of state action frequencies. Right, and so the comparison between these two methods, so both of them seem very natural, okay, as choices of natural gradients for policies. And the comparison is just that, if you look at Kakae's method, this could be obtained from Morifura's method by subtracting here the Fisher information metrics over the state distributions. So we have these joint probability distributions, and somehow we were going to be taking out the Fisher metric for the margins over the states. And more generally, if we were to look at these Hessian natural policy gradients, we would define them just using our Hessian geometry. So we define this Riemannian metric will be given by our Hessian. Right, so and for the functions that I showed you before for this Hessian geometries, defined in terms of sigma, we then recover for sigma equals 1 the Fisher geometry, which means we recover the Morimura's natural policy gradient, and for sigma equals 2, the Itakura's item, for sigma equals 0, the Euclidean geometry. All right, so then let me tell you briefly about convergence of natural policy gradient flows. So the idea here is that we can reduce the evolution to a state action space. So we look at these dynamics of the parameter over time as given by this natural gradient of the objective in parameter space, which is given in this way. Then this is a gradient flow with respect to our Riemannian metric on N. This is our space of state action frequencies. Now we look at the evolution of the state action frequency as given by that Riemannian gradient of the objective in that space. So now we want to use this picture to study convergence of the unregularized Hessian natural policy gradient flows. So we have a couple of settings here. I'm going to spare you the details for now, but we can return to this afterwards if you're curious. A couple of technical details, they're not too bad. But then, we can show in a general case a global convergence of the Hessian natural policy gradient flows. So it's given in this form. So if we take any state action frequency eta, the objective value there compared to the objective value at time t is going to be less than something that decreases with t. So ultimately, we could pick in here the optimal eta. So then the difference to the optimal eta is going to drop to 0 as t goes to infinity. Okay, so this is similar to some previous results, but what this actually tells us is that all we need to do, so given this, if we wanted to obtain global convergence, what we would need to do is to show that, or to ensure the well-posedness of the problem. So in a sense, by presenting this perspective of state action frequencies, we can leverage certain results that are kind of general here for Hessian geometries. To induce Hessian geometries that prevent some problems, we consider what we call here Legendre type functions, and that satisfy some conditions. Essentially, they are saying that there is some smoothness and convexity that is valid, at least in the interior of our search space, and there is a gradient blow up at the boundary. So this is going to prevent the solution trajectories from hitting the boundary of our polytope in finite time, in which case they would not be able to follow the path all the way to the optimum. So a couple of examples here already mentioned, the Kakai natural policy gradient and so. So based on this, we can verify the convergence of Kakai's natural policy gradient flow for an unregularized reward, and it has this kind of decay rate. We can also verify the convergence of the sigma natural policy gradient flow for the unregularized reward. And so we have this difference goes like this, depending on what was the sigma that we're using to define the geometry. There's an entire family of cases here. So maybe a remark to make here is that these theorems are giving us the global convergence for these natural gradient flows to a maximizer of the original objective, and not of the regularized objective. And the reason why they are able to do this is because we are still optimizing the original objective. All that we have modified is the Riemannian metric, but we have not modified the objective function. Therefore, we're still converging to the global optimum of the original objective. This is kind of useful or interesting. We're also able to obtain some improvements of these rates, both for the sigma and the Kakai natural policy gradients. Linear convergence for the unregularized Kakai natural policy gradient flow. So you see the rate here is linear. Linear convergence for the Morimura natural policy gradient flow. Some improved rates for the sigma natural policy gradient flow. Here this is linear. You see D appears in the exponent. This for sigma equals 1. That corresponds to the Morimura natural policy gradient flow. A couple of examples. This is a toy example where we have states, 2 states and 2 actions, and instantaneous rewards given here. It's a baby example, but just to give you a sense of what this might look like. So here, this is the simplex of joint probability distributions over states and actions, and in there we have this other polytope in black. That is the space of feasible state action frequencies. And here for different initial distributions, we see these optimization trajectories for the ordinary vanilla policy gradient. The optimizer is sitting in this vertex. So the instantaneous reward is a vector pointing that way. So we have some kind of a objective that is maximized in here. Kakai natural gradient works like this for our sigma geometries. You see these trajectories actually hit the boundary in finite time and stick there. That also happens for Euclidean, sigma 0.5. For sigma equals to 1, that's the Morimura. You see these trajectories actually, nicely go to the optimum. And you could argue that, like these trajectories in the case of Kakai's natural policy gradient, they are, you see, they are walking all the way out there before they actually move towards the optimum. So some of these trajectories with the Morimura actually seem to be going a little bit straighter to the optimum. So actually you could interpret this as some kind of a plateau. And plateaus are the type of problems that you may want to address or resolve when you're using natural gradients. And it's just a couple more examples here. This is now plotted over the space of policies. So remember, we have the mapping from policies to state action frequencies and into the reward. And in this space, maybe it becomes more apparent that some of these trajectories are doing a very funny movement here. But for Morimura, they are a little bit straighter. So we look at the rates here, and in these numerical examples, they align with the theoretical results that I showed you. Like for Fisher, it's a linear rate, and also for these other values of sigma. So this is a log-log plot. Excuse me, a log plot. And so for Kakai, we also have this convergence. For other values of sigma less than 1, we have a convergence in finite time, and maybe not to the global optimum. Okay, so I'm going to go a little bit quickly over this because I still want to show you maybe a little bit of the discussion because before wrapping up. But morally, so when we look now at regularized cases, we are able to prove linear convergence. So this is a general result for the linear convergence of regularized objectives. And so based on this type of results, which tell us that the distance between the optimal parameter of the regularized objective and our parameter of time t for a regularizer, eta. So we're just doing the gradient of this method with the Hessian geometry induced by this regularization, and we get this linear convergence. And we get these corollaries for the Kaka natural policy gradient flow, for the sigma natural policy gradient flow, so here this linear rate. And in the case of finite step size optimization, we are able to show quadratic convergence for the regularized natural policy gradients. So now we have finite steps here. And in these cases, we get the locally quadratic rate of convergence. This is using inexact Newton methods and the corresponding description of the natural policy gradients that we have kind of developed here. All right, so to quickly wrap up, there's a bunch of individual results, so maybe summarizing this table. So there are different types of geometries that we may try to define or consider natural. So we try to cast them, all of them, as coming from natural structures in the space of state action frequencies. And from that perspective, we can very naturally study the convergence of gradient flows and gradient descent methods with an unregularized objective or with a regularized objective. And we obtain a series of new results showing linear convergence of some of these methods and quadratic convergence for the discrete time setting. So why is the analysis easier in state action space? I mean, this was the whole idea here. So just to reiterate that, in state action space, the problem is strongly convex, whereas in policy space, or even worse, in parameter space, the problem is actually non-convex. So actually proving global convergence of the optimization method in policy space or in parameter space, still possible, but potentially much harder. Some of our proofs will recover in some of our calculations, some of previous existing results, but maybe with shorter proofs. Further, in policy space, the corresponding Riemannian metric might not be the Hessian metric of the regularizer. So when we're looking at these regularized problems, and by considering the correct space, we can look at this Riemannian metrics as being the Hessian metric of the regularizer, which allows us to leverage certain techniques. In the parameter theta, the natural policy gradient algorithm can be regarded as a generalized Gauss-Newton method, but the reward function is non-convex in parameter space. Then for over-parameterized models, like when the dimension of the parameter is bigger than the dimension of this model space, the Hessian is not positive definite, which may complicate the analysis in parameter space. But in model space, things are just naturally well. Okay, so in the conclusion, we study a class of natural policy gradient methods that arise from Hessian geometries in state action space. We prove linear convergence for Kakares and Morimura's natural policy gradients for the unregularized reward and locally quadratic convergence for the regularized natural policy gradients with respect to the Hessian geometry of the regularizer. It's a lot of interesting problems and questions that we are actively looking at, like general parametric policy classes, and particularly the case of partially observable Markov decision processes, and further improving or developing new policy gradient methods without plateaus, and also studying natural policy gradient methods in state action space with estimation, where maybe this Q value function, we actually need to estimate that, and there are some statistical considerations to keep in mind. Okay, so I'm going to stop here.